Today we are going to give a very interesting presentation of a proof journal from OSU classes Math 3345. It's about logic. And today we are going to prove that the set of all infinite sequences consisting of zeros and ones is uncountable. And first, we recall that what is called countable. A set S is called countable if there exists an injective function from S to the natural numbers. And also, we will use an argument similar to Cantor's diagonal lemma to prove this, to complete this proof. And now, let's recall what is Cantor's diagonal lemma. So, basically, it's about the uncountability of all real numbers. But instead of considering the whole real numbers, we will only look at the open interval 0 to 1, because if 0 to 1 is countable, then all real numbers is countable. And this lemma talks that let f be any function from natural numbers to the interval 0 to 1, then there exists a number y which is an element of 0 to 1, such that y doesn't belong to the range of f. So here is our key ideas. We define a function f from natural numbers to the open interval 0 to 1, and we wish to find a number y which is an element of 0 to 1, such that y is not an element of the range of f, which are f1, f2, f3, f4, and so on. And if we can find this number y, then this implies that f is not a surjection. The most important point in this proof is to write all fn in the standard decimal expansions, so we can find a number y in its decimal expansion to make it different from all fn. And here is our proof. First, let f be any arbitrary function from natural numbers to 0 to 1. And we are going to find a number y which is an element of 0 to 1 such that y isn't an element of range of f. Now look at this table. For each n is an element of natural numbers and each k is an element of natural numbers, we let x sub nk be the kth digit in the standard decimal expansion of fn. So look, for example, we look at this table. Here, the x sub 13 means it's the third digit of decimal expansion of f1. So now we are going to find a number y which is different from all, which should be different from all range of f, which is f1, f2, f3, f4, and so on. And we can, and by the observation that we find a number y by defining the digits in its decimal expansion. And we let 1 be the number whose standard decimal expansion is y equals to 0. Y sub 1, y sub 2, y sub 3, and y sub 4, and so on. And we define y sub n equals to 5 if x n doesn't equal to 5, and y sub n equals to 6 if x n equal to 5. So for each n belongs to is an element of natural numbers, y sub n is not equal to x sub n. And because of this, so y is not in the range of f, so f is not a surjection. For example, here, the first digit of f1 is x sub 11. But for our definition of y, the first digit of y doesn't equal to x11 and the second digit of y doesn't equal to the second digit of f2 and so on. So we can verify that y isn't an element of the range of f. And we complete our proof of the Cantor's diagonal argument, and now we will prove that the set of all infinite sequences consisting of zeros and ones is uncountable.
Okay, to prove this claim, the key idea is to prove by the weight of contradiction. We suppose it is countable, which means that there exists an injection uh, from the set of all infinite sequence consisting only zeros and ones to the set of natural number. Then we'll construct a sequence that does not uh, have a natural number to map to. Then we can reach a contradiction. So for the proof, um, firstly, we suppose that uh, it is countable from the set of all infinite sequence consisting only zeros and ones to the set of natural number, and which means there exists a function f such that f is injective from S to N, where S here we denote it as the set of an infinite sequence consisting zeros and ones. Then we denote uh, S1 as a sequence of S sub 11, S sub 12, S sub 13, S sub 14, and so on, and S2 as S sub 21, S sub 22, S sub 23, and S sub 24, and so on. For for S sub nk, it means the kth term in a sequence of Sn. Now we further assume that fsn is equal to n, which which is an natural number. Then we want to construct a sequence T that is not in this range. We let T be a sequence of T1, T2 to Tn, where Tn is equal to y minus s sub nn, since s sub nn can only equal to 0 or 1. So 1 minus s sub nn also equals to either 0 or 1s, but y minus s sub nn can never equal to s sub nn. Also, T is an infinite sequence consisting of zeros and ones. This means that T is an element of set S, and also it is true that Ftn is equal to a natural number k. However, since we found that there always exists a term in sequence T uh, that is not equal to uh, any sequence of Sn, and since S Fsn is equal to n, so which means Ft equals to k is not an element of set 1 to n, and this set is the set of natural numbers, so k is not a natural number. Here we reach the contradiction that k is a natural number and k is not a natural number. Hence, we can conclude that it is uncountable from from the set of all infinite sequence consisting of zeros and one to the set of natural number. Okay, here is an example about countable set. We let set S equals to A plus BI, where A, B are integers and I is an irrational numbers. We want to prove that S is countable. To prove this, we need to find an injection from S to the set of natural number. So we define a function f from S to n, where f a plus bi is a piecewise function, and f a plus bi equals to 2 raised to a times 3 raised to b for both a and b greater than 0, and 3 raised to a times 1 over 5 raised to b for a plus a greater than 0 but b less or equals than 0. It equals to 1 over 7 raised to a times 11 raised to b for a less or equal than 0 and b greater than 0, for it equals to 1 over 13 raised to a times 1 over 17 raised to b for both a and b less or equal than 0. Since I is an irrational number, and so for example, a1 plus b1 I equal to a2 plus b2 I only if a1 equal to a2 and b1 equal to b2. And for each case, it is impossible for both AB equal to the AB in another case. So um, so for each case, A and B is unique, and we know that uh, a natural number can be written as prime factorization, and so if and so for each case, the result is not the result is can never equal to the result in another case. So we construct such a function that distinct input yields distinct output. So we prove that S is countable. That's it.